Hello, everybody. So we're starting now the last session. We've got 3 talks all related on the topic of PGas middleware, and I am the bottom of the stack below the next 2 talks, so I'm going to do a little bit of introduction, not just of my own work, but I'll lead into the next 2 talks in a little bit. So first, I just want to talk about PGas in general. You did hear a little bit about this from DK Panda on Tuesday when he talked about MFPitch X, which is their effort to provide MPI and PGas runtimes unified. But he gave a much shorter introduction than you might want if you actually want to, be a developer in PGas. And I'm also going to cut things kind of short. So if you're really interested, you'll find a pretty good description in the Wikipedia and links from there. But for our purposes today, PGas is a programming model, an alternative to message passing, that is MPI, for HPC programming. And 2 of the examples are UPC++ and SHMEM, which will be the next 2 talks. All of them have in common, they provide some sort of a shared memory style programming that can run either in true shared memory or in distributed memory environments, which is where I end up at a interconnects related talk. In the case of Unified Parallel C, which is abbreviated UPC, this shows up in a pointer to shared. So it's a dialect of C, and there you have a shared keyword that you can attach to pointers, and then these pointer types can span between the nodes, but you dereference it the same way you would any other pointer, and you have arrays as well. Fortran 2008 introduces coarrays. Those are arrays that also span nodes, and in that case you have a slightly different array syntax notation for one or more of the dimensions that are known as codimensions as you walk across the arrays. And of course, many different variations, there'll be a longer list of these in the next slide, provide many different ways to expose this PGas programming paradigm. The partitioned in the name comes from the idea that there is a global memory, but it is partitioned into pieces that have affinity or closeness or association or whatever the term might be to different threads of control. So you have some awareness of this that allows you to write locality-aware code and therefore avoid communication and achieve things you wouldn't necessarily if the distribution of your objects or your array elements or what have you was completely transparent and outside your control. More recently, there's been an emergence of a subclass known as asynchronous PGas or APGas that extends the idea of this global memory with the idea that you can spawn tasks asynchronously, both locally and remotely, and Cray Chapel and IBM X10 are a couple prime examples of that work. So as I said, GASNet is one of the software layers that makes up several PGas runtimes. It is itself an acronym. GASNet is Global Address Space Networking. It focuses, unlike MPI, which is mostly about message passing and has only recently introduced a very strong remote memory access API, its focus has always been on RMA, put and get type operations, as well as an RPC, remote procedure call mechanism based on Berkeley active messages. This project has been a joint project of the University of California, Berkeley and Lawrence Berkeley National Lab, and we've been at it since 2002 when this began as part of the Unified Parallel C and Titanium projects, 2 PGas languages at the 2 institutions. It's highly portable. It runs on everything from laptops to supercomputers. It runs on ARM and Spark. It runs on Linux, Mac OS, FreeBSD, OpenBSD, NetBSD. It's run in the past on various other OSs that were IRIX and things like that are no longer in wide use. And because of the long lifetime and the great portability, it has become a de facto standard in its field. I'm not going to read that list to you. It's just there either if you want to look at the slides later. It's not even entirely complete, but it's just supposed to impress you with the size of that list, of course. So GASNet itself is an API that's split into 2 levels. We have at the bottom what we call the GASNet Core API, which includes the active messages, the remote procedure call interfaces. Active messages is a restricted form of remote procedure call. An active message request goes from an initiator to a target node, and that target runs a handler. We register handlers at initiation, so we're talking about passing an integer index, not an actual function pointer. And so there's, like many RPC mechanisms, a little bit of a protection there. You're not passing random addresses and such. There's a restriction in that a request handler is permitted only one form of communication. That is, it can reply back to the original requester. It cannot perform multiple replies, and it cannot perform any sort of requests or gets or puts to any nodes in the system. Porting this active message implementation, this core API, to a new platform is the minimum requirement for supporting a new platform, a new network. Above this core API is the extended API, and that includes all of the remote memory access, RMA. I will sometimes say RDMA. This is the remote get and put operations. So one-sided operations in which the caller will provide both the local and remote virtual addresses as well as the length. We include both blocking operations where you put and it returns only when the data has reached the target HCA or the target memory system at the other end. We've already gone through those things with the persistence talks. We have implicit and explicit handle-based non-blocking operations. So explicit handle is I call a non-blocking put and give you a handle and use that handle to poll or block for completion. And region-based implicit, basically you can do put, and a sync call that waits for all those puts that preceded it since the last sync, or you can actually define regions where you say begin region, put, get, end, and that end returns a handle that you can then sync or wait on. So you have some flexibility. These types of things are mainly intended for compiler-generated code where it may take some mechanisms to bundle together things into a single handle, a single object to track communication that was initiated with multiple operations. Also in the extended API is a split phase barrier, so a non-blocking barrier with a separate notify that you've arrived at the barrier and wait for everyone to reach it. There is a reference extended that implements all of the things I've discussed there in terms of that core API, in terms of active messages, and that's why I said that the active message core API was the minimum requirement for a new port. However, for performance, you don't want to rely solely on that, and so native implementations in terms of underlying API usually replaces that. And so we'll talk about two of those as I go forward in the talk. GASNet also currently includes extensions for collectives and for what we call VIS, vector index strided. And those are so for non-contiguous data transfers that come up, for instance, when you have ghost zones, areas at the edges of 2, 3, or higher dimensional arrays that need to be transferred to a neighbor in a decomposition in space. So I'm going to talk a little bit about the historical pre-OFA days. The original implementation of GASNet for InfiniBand was over the Mellanox Verbs API. It first appeared in the October 2003 release. The work actually started July of that year, which makes our InfiniBand support approximately a year older than the OFA, which was under another name when it was founded in July of 2004. So we've been at this longer than this organization. We did finally retire the Mellanox VAPI support 10 years later, and the October 2013 release was the first release not to include it. I'm just going to talk a little bit here about the basic design because it's carried forward to all of our other APIs since then. The active message, as I said, is transmitting this remote procedure call that can carry some arguments and payload that I won't go into the details on. And so the primary mechanism we used to implement the GASNet active messages on InfiniBand is a send with immediate operation. And the immediate just gives us a little bit extra. It takes 32 bits that would have been otherwise part of the send payload, and makes use of the fact that that header's there. We use some of our header information in that. And we use a credit-based flow control for these so that we never see a receiver not ready NAC on the wire. This avoids some bad network behaviors when you have all-to-one or many-to-one behaviors that might overrun a particular receiver. We also have, for some better efficiency, mechanism that pulls in memory rather than relying on a completion queue entry. That uses an RDMA write. We do this for a small number of hot peers because we want to pull only a small bounded number of locations in memory. And this is not an optimization unique to us. This has been done in MVPitch in DK Panda's group and experimented with in OpenMPI as well. There's just no getting around the fact that completion queue is not free. In terms of the extended API, the get put operations, the common or preferred case, and I'll elaborate on this more in a later slide, has I should probably say remote rather than destination. The remote memory, so that's the destination of the put or the source for the get, in memory that's been registered initialization. So we're able to use what I thought at the time were thin wrappers before OFI came around RDMA read and RDMA write operations. We basically have both addresses and an R key that corresponds to the registered memory, hopefully the entirety of the registered memory at the remote node, and so we're able to quite conveniently translate the arguments we're given into the necessary fields in the work request. And the work request ID field gives us a nice way to map the completion queue entry back to our operation and tracking completion and things like that. So at the time, it was a relatively simple implementation. Things got more complex as we went forward, for instance, adding a little bit more code to use the inline send as an optimization when it was available. And one of the more complex things, I mean, the only thing that was more or less, it felt like it shouldn't have been necessary, but it was we ended up needing to track the number of entries we were using in send queues and completion queues to avoid overruns. So basically sort of semaphores, so that we would decrement that as we used resources, incremented as we removed entries from the completion queue, and we would have to spin poll on the completion queue to recover entries if one of those semaphore values reached 0. And that was probably one of the, the least obvious requirements to get things right, because you may run for a long time in a code and never encounter a CQ exhaustion, but once you do, things kind of fall apart. So I mentioned I would talk about the desired or common case. So GASNet has a requirement that the remote address you present in one of these RMA operations has to be in what's referred to as the segment, which is a range of memory established at initialization time. But there are a couple different modes you can build GASNet in depending on what your runtime expects to use. For Unified Parallel C, there's a distinct UPC shared heap that memory allocation for remotely accessible objects come from, and so we use what's called the fast mode in GASNet. And so the entire segment is one contiguous virtual range of memory that we just mmap something and register the entire thing. We share those R keys at initialization, and the common preferred case I mentioned on the previous slide occurs. However, we also have what's known as an everything mode, where there is no specific range. Essentially, it runs the whole address range is your segment. Obviously, you can't pre-register that with the HCA because, well, the resources don't exist to instantiate a page frame for every bit of the virtual address space, and we don't know necessarily at initialization time what later addresses your malloc or mmap or whatever is going to allocate. So we end up needing to work with a little bit of dynamic registration, and so this ends up being used when either the source or destination is not pre-registered. In fast, that can still occur with the initiator's address, the local address. For instance, I'm doing a put, the source of which is a malloc or stack variable, and in everything mode it recurs for all local and remote addresses at least once, hopefully at most once if we're lucky. I should note that we avoid dynamic registration when possible. For instance, immediate send for things that are small enough, and bounce buffers can also be used either for gets or puts to avoid registration at the initiator's end. So there's a paper citation down there at the bottom for more detail. We developed something we call the Firehose library. It's not specific to InfiniBand. It was actually originally developed for MirrorNet GM, but we've also used it in several other networks as well. And it exposes one-sided 0 copy as the common case, and it degrades gracefully to a rendezvous as the working set grows to exceed the available resources. Basically, it's doing dynamic registration at both ends, and by partitioning the resources available among your peers, I would give ownership of a fraction of my pinning resources to each of my peers. And so they can cache that fraction of my information without fear that I will invalidate it without their prior knowledge. So they own or they remote control a portion of my registration resources. Unfortunately, this is not infinitely scalable because I can't partition 128,000 max number of registrations among 1 million peers, for instance. It's also susceptible to certain errors when we've cached something. We've cached that a virtual address corresponds to a particular R key, but the malloc library, when you free an object at maybe 2 levels of software above us, that may be unmapped, and malloc may again map that same address later, and we will be using an R key that corresponds potentially to a completely different page frame than the user gets with the same virtual address. And strange things happen because it looks like the transfer succeeds because the OS had a reference on that page frame, it didn't release it, and the HCA is successfully moving stuff in and out of a page frame that has no mapping into the application. And I will come back to this particular issue because it is important. One of the other things that we did, I said it started simple and it grew. These active messages, these RPCs, they do have to run on a host CPU. They will run synchronously when you make certain calls into GASNet, including GASNet AM poll to poll for active messages. But optionally, we can also have a progress thread to run these asynchronously, particularly important if you're doing things that require the other end to be attentive, for instance, acquiring locks in UPC, while the other end may be doing something computationally intensive and not actively polling the CQ. In general, the RMA operations proceed completely asynchronously because we've ensured that we don't we don't have a side queue. We blocked on that semaphore, as I talked about, until the send queue had room to accept our work. However, as I just mentioned, we have this fire hose mechanism that's being used in the everything mode. So there may actually be an active message-based round trip to do the remote pinning in that case. And so the ability for me to do a put into some remote address space actually does depend on its making progress on active messages, at least the first time I use a given range of addresses. So in the VAPI conduit, this, whatever is 12-year-old now technology, we use the things that were provided by Mellanox at the time to set up the ability for a thread to basically go to sleep blocking until things showed up in the completion queue. Unfortunately, we failed at that time to actually find it to be beneficial. Very few things that we had in terms of applications were inattentive, that is, not making calls to GASNet AM poll or their GASNet calls, enough that this was a good improvement. In fact, what we found that for applications with very good network attentiveness, it tended to slow things down. Contention either for the CPU itself, but more commonly for locks, caches, et cetera, between the application and the progress thread. It just didn't work out so well. Keep in mind this was Pentium 4 technology at the time. And I think we'd only just recently gotten our first IB4X HCA. We've been on the 1X Mellanox cards before that. So this is quite some time ago, and things have changed. So that's the old story. What's the new story? So there are 2 libraries to talk about at this point. We got the libverbs and the libfabric. Let's start with the verbs. So this is known as IBV conduit for the prefix in the library, and it first appeared in October 2007. For its first, whatever that came to, 6 years, there was a single source base shared by the VAPI and IBV conduits with ifdef and typedef to hide the differences where they were necessary to make distinctions. Because they're both relatively good mappings of the verbs specification from IBTA, there actually was essentially no significant algorithmic difference between the two, just different data structures, different calling conventions to do the same things. And therefore the fundamentals of the design didn't have to change. However, over time, the code grew to take advantage of things that were not part of the original design. And I think the first 2 are probably, I don't need to do any evangelism for them. Shared receive queue and XRC were both designed as mechanisms to conserve resources and to scale out to larger jobs. And we found, even at the scale of something like TAC Ranger, if you're familiar with that system, it was absolutely necessary to look at 4K processes across that system, we were essentially, with our default settings, posting nearly all of the memory on a node to receive queues and leaving none for the application. Now, we could scale our usage back a little bit, changing environment variables, but the active message being, we're talking about n squared allocation globally. Every pair needs memory to buffer because you didn't have the sharing of receive queues. And so SRQ solved one scaling bottleneck there. XRC was similarly a problem. If I took those same 4K processes, those were on 4,000 nodes, and I tried to run all 16 cores of TAC range, or 64K processes, well, the HCAs on that system were configured for 64K queue pairs, and I needed exactly that many, and of course, the subnet manager takes some resources, and the file system may take some resources, and basically, it did not run. There was not resources available to run that, and so XRC, with its scaling improvement being proportional to the square of the cores, a 256-fold reduction, was the only way it would work there, and it's made a huge difference. Now, there are two XRC APIs out there, the Mellanox one and the one that made it its way into OFED, and we currently do support both of those. Some of the other things that have come along that have distinguished the Verbs from what we did originally in VAPI, again, related to the scalability issues, lazy connect. Instead of connecting, we are using RC, but instead of connecting all of the queue pairs up at initialization time, just doing it on demand as peers actually communicate, only build the reliable connection queue pairs at that point. Reducing both the memory associated with buffering as well as the consumption of queue pairs. And asynchronous progress has come back, and we find now that it is efficient. It is not providing a new source of contention or a source of slowdown. And so we're pleased to see that something that technology has made what we thought was a good idea actually into a good idea now. So LibFabric is one of the newest conduits or networks supported in GASNet. I'm afraid I can't say as much in detail about it because while I was the author of the VAPI and IBV support, the OFI conduit was contributed by Intel. It first appeared about 6 months ago, this last October, but it had been around for about a year before that at least, originally known as SFI conduit. There's a paper cited down here at the bottom describing in detail a bit more about its design, and at least 3 of those authors either have been or still are in this room, so bug them if you have questions. But the paper did show significantly better mapping between the GASNet API and OFI instead of IBV. That's expressed not only in the cycle counts as they measured and reported in that paper, but also just a simple lines of code metric shows that at this point IBV conduit is 12,500 lines and OFI conduit is 2,500. So 80% reduction. I can't say that they're exactly feature compatible or feature equivalent and things like that. And one's much younger and hasn't had time to grow workarounds for buggy providers and things like that. But just to sketch the design, the core API, active messages, uses the reliable diagram endpoint types and uses the FI message and FI multi-receive capabilities. I believe it could do without the multi-receive at the expense of more memory. The extended API for RMA is using a distinct, separate reliable datagram endpoint and a distinct completion queue for collecting the completions there. And in particular, one of the optimizations made is that there's a counter that indicates whether or not there are any extended API operations in flight, and it skips polling that completion queue if there's nothing that could possibly complete there. The required capabilities here are the FI RMA capability, and subnet registration uses MR Scalable. Some of you probably memorized the provider feature support table, but for those of you that haven't, currently the only providers that implement MR Scalable are the sockets provider, which by definition provides everything, as well as the PSM and PSM2 providers from Intel, which is, again, where this was developed at Intel. So at this point, personally, I've only had the opportunity to run and use this code with a sockets provider, but I'm looking forward both to getting access to OPA hardware, as well as I know that the GNI provider is working on providing MR scalable support in, I can't say near future because I don't know what their timeline is, but it's one of the things that's at the top of their list. So going on to talking about quickly what we're doing now and doing in the near future. So GASNet is roughly 15 years old in terms of the API design effort, and we're going through an effort now to modernize that, incorporating the 15 years worth of lessons learned, as well as recognizing how significantly the landscape has changed. At one point, SMP support was a configure time option because most of our nodes were single CPU and the word core didn't exist yet. Now we're looking at hundreds of CPU contexts per NIC. We're looking at tens or hundreds of gigabytes of memory per NIC. And the move in the languages and library space from the conventional PGas or classical PGas to these asynchronous PGas has changed some of the requirements, some of the usage models for how GASNet operates. And in the interest of time, I won't read these off and try to explain them. But we're taking this opportunity to support multiple clients, to provide resilience features, and making threads first-class entities, in part because of the APGas languages. Again, my time's running down, so I won't try to read everything in extreme detail. But we are working very hard on resilience as one of the focus areas. And so this includes providing something other than assert as a mechanism for error handling. In particular, the GASNet API, GASNet EX API, provides a mechanism for registering error handlers, callbacks, where the code above us, we refer to that as our client, where the client code can register code to be invoked with information about the operation that failed and the nature of the failure, and give mechanism rather than policy for recovery from errors. Part of that, of course, we have to be resilient. We have to not leak memory, not assert. So there's a significant effort to be done to basically go through and replace assert-type failure modes with something more like a C++ throw, except that we're written in C, so the unwinding from the, I've acquired this resource, and this resource, and now I need to free them as I march back out of the stack. All that has to be done far more manually. One of the things I'm more excited about, I've been working on checkpoint restart. BLCR is the software in the Linux kernel for a long time now, as well as GASNet. And I finally have had the opportunity to bring those two pieces of work together. We have a release coming up, hopefully in no more than 4 or 6 weeks from now. It'll be the first one to feature support for checkpoint restart with GASNet. Pretty much just our UDP conduit, which is like kind of like our sockets provider, and the IBV. But we have more work going forward in the checkpoint area. Future work, we're definitely excited about being able to take advantage of ODP to get out of the business of messing with all this caching of remote registrations and things like that, and have someone better positioned in the kernel, in the hardware, in the firmware to do these sorts of things. As part of the resilience work, we want to pick up automatic path migration as something that we've just never had the need or motivation to expend effort on, and now we have resilience as a target, so that will be something that we want to focus on. And also, we've never taken advantage of multicast groups, but they're definitely something we can be making good use of for resilience, especially if you've migrated something. The best way for it to be rediscovered would be via some of the multicast mechanisms. Within OFI conduit, we'd like to see the checkpoint restart support we've developed for IBV extended to OFI as well. But other than that, I'm not in a position yet to judge what other sort of work needs to be done. Questions?